Hello everyone. Welcome back. Let us see what we have discussed so far on the topic time value of money. So till now what we have seen the relationships between the various type of cash flows, that is the relationship between future worth and present worth, the relationship between annuities and present worth or future worth. Similarly, the relationship between arithmetic gradient and the present series or the future series or the annuities. So this is the summary what we have discussed so far. So today in this lecture, I will try to extend whatever we have discussed so far in solving the cash flow problems. My emphasis will be to solve some of the problems, equivalence of the cash flow problems using the relationships which we have studied so far. So let us see a problem. So this is a problem based on the cash flow, and this is problem from the book of DeGarmo and problem 3.55 on page 132, of course unsolved. In this problem, the two cash flows are given and we have to find out the value of K so that the above and the below these two cash flows, they are equivalent or they are basically representing the same monetary value. So let us see how to solve this problem. So let us see how we can solve the given problem. So there are two cash flows. Let me call the first cash flow, the above one is A. So in this, the cash flow is for 5 years, 0, 1, 2, 3, 4, 5. And there are two transactions of $K each. First one at the end of 4th year and another one is at the end of 5 years. Fine. So I can visualize this cash flow as two separate cash flows, each depicting a single transaction. Each depicting a single transaction. Fine. Now, what I can do, I can find out that what is the equivalent of this K at time t equal to 0. So what I am interested in, I am interested in finding out the equivalent of this K at this point of time. Similarly, the equivalent of this K at this point of time. Okay, let me draw a dotted line here. So I am calling this as PA1 and I am calling this as PA2. Now to recall, we have a relationship between P and A as F equal to P1 plus I to the power N. So if I just fill up the numerical values to find out what will be the equivalent worth of this K at time t equal to 0, or I can find out the equivalent worth PA1 of this transaction K. So PA1 is nothing, it will be F upon 1 plus I to the power N. F is given as, in this case it is given as K, and I is given as 15%, so it will be 1.15 to the power 4. So these are for 4 years. So the best way is to count like this: 1, 2, 3, 4. We'll see this is why this method is sometimes preferred. So this is PA1. On similar lines, Similarly, we can find out PA2. It will be nothing but K upon now 1.15 to the power 5. So if I am interested in finding out the net worth, that is PA, so 0, 1, 2, 3, 4, 5. So this PA will be PA1 plus PA2. So this is K on 1 upon 1.15 to the power 4 plus 1 upon 1.15 to the power 5. So if I just compute the value, this comes out to be $1.0688K. So this is PA, or what I have computed is the net worth at time t equal to 0 for this cash flow. So this is quite simple. The relationship between P and F is used for computing the equivalent of these 2K transactions at this point of time. Fine. Now let us look at the second cash flow diagram. So a second flash cash flow diagram looks like this. Okay, let me draw it. 0, 1, 2, 3, 4, 5, 6, 7. So if I draw it, the first transaction is 100 here, then I think 210, then 320, then 440, then 550, and then 660. At the first instance, it's look like that it is a gradient series because the transactions, they are increasing. But if I take G to be 100, it should be, for this series to be a gradient series, this should be just 200 and this should be 300, but rather here it is 210 and here it is 320. So really it's not a standard gradient series for which we are having the relationship. Again, what we can do is, in a very simple case, we can just treat each transaction as a single transaction and compute the value of each transaction at this point of time at time t equal to 0 and equate the two. So that is one method of solving the problem. But at times, if we have the cash flow for large number of years, then sometimes treating every single payment as a single payment becomes a tedious task. So let me solve it in another way. So if I draw a line here, fine. So now what I can do, I can split this cash flows into two. 0, 1, 2, 3, 4, 5, 6, and 7. One cash flow which is below this yellow dotted line. Now if I just draw this, the first transaction is starting here, 100. Another one will be also 100 and continue till the end. Every transaction is 100. And the second series is what we can have from this is 0, 1 2 3 4. So if it is this 100, we don't have any transaction at the second year, rather we have the first transaction here, which is of 110, because 100 we have already taken here. So what remains out of 210 is just 110. Then we have 220, then we have 330, then we have 440, and finally at the last we have 550. So I think at this point of time there is no problem. What we did, we have just split these two series like this. Now again, if we see, can I call this series as a standard annuities? The answer to this is no, because if I recall the standard uniform series or annuities, the first transaction starts at t equal to 1. But here in this series, we are not having any transaction at t equal to 1. So a very easy way to manipulate this series so that whatever standard formulas we are having, that we can utilize. Okay, let me draw this series like this. So okay, so if I write this as 0 1 2 3 4 5 6 7. Okay, so just forget about what we are having on this side. Just forget about this. So what we are having a series starting at this point and continuing at this point. Now actually this is 1, so if I rewrite these years, so I may rewrite this as 0 1 2 3 4 5 6, just to make a standard one. And again we are having the transactions, equal amount of transactions, $100. Fine. Now if I just look at this series, forget about this end of years 2 3 4 5, you treat this to be starting at 0, and instead of 2 it is 1, like this. If we have this standard series, I have the relationship available, that is, if I am interested in finding out the present worth of all these transactions or the equivalent worth of these transactions at this point of time. So this, how we can find out? We can find out by using the relationship, that is P equal to A 1 plus I to the power n minus 1 upon I 1 plus I to the power n. So this is the relationship. So let me call this as PB1. Okay, PB1. If I just put the numerical values, A is given as 100 and 1 plus I, this is 1.15. Now count the number of years, 1 2 3 4 5 6. So if we compare it with an initial one, it is coming out to be 7, what is written here. But since I have told you, just forget about these of end years, treat it like this, 0 1 2 3. So it will be 6 minus 1 upon 0.15 bracket 1.15 to the power 6. So if you compute this, this comes out to be $3.378.44. So at this time, what we have done, we have just focused on the cash flow which is starting from this point and ending here. So instead of 7 years end of year's life, we have manipulated it for 6. Now just look at this particular cash flow, that is before this zigzag line. So now what I am having here it is 0 and here it is 1. So what I am having is the net equivalent of these annuities at this point of time, and the monetary value of this is $378.44. Right. So now if I just look up at this series, this is a single transaction type of series. F is known. I can find out what will be the value of P. So if I call this as PB1 dash, it will be equal to F upon 1 plus I to the power n. Just writing down the numerical values, F is given as this divided by 1.15 to the power, in this case it will be 1. So if I just compute this comes out to be 329.085. Check my calculations. Fine. So this is what we have done. We have computed the equivalent worth of this equal transactions. Of course, the transactions, they are not annuities because the first transaction is not starting at time t equal to 1. So, but somehow we have manipulated this series so that the standard formulas that are available for the standard series that are applicable. So in that way, what we did, we have computed the equivalent worth of these equal end of year transactions. First, starting at the end of year 2, we have come and continuing till the end of 7 years, we have computed the equivalence of this at time t equal to 0. So this is one thing. Now coming on to the next series, again, if you see here, this is not a standard gradient series, because if it is a standard gradient series, the first transaction must take place at this point of time. But here, in this case, we don't have any transaction at this point of time marked as red. So what I can do on similar lines, I am drawing a zigzag line here. Now instead of 0, I am calling this as 1, this is 2, this is 3, this is 4, this is 1, okay, sorry, this is 0, this is 1, this is 2, 3, 4, 5 and 6. Fine. On similar lines, what we have done for the previous series. Now if this is the case, the gradient series looks like G, 2G, 3G. So if I say this G, 2 times of this is 220, so this is 2G. 3 times of this is 3G. So that means if I take this as the end of years, and if I assume that my cash flow starts from here, treating this as the initial point, that is the time t equal to 0, this is a standard gradient series with G equal to 110. Now, if I just, since this is a standard series, I can use the standard formula between P and G, what we have discussed in the previous lecture. So if I just rewrite it, P is nothing but G, okay, bracket 1 plus I to the power n minus in minus 1 divided by I square 1 plus I to the power n. So this is what we have seen on the previous time. So if I just put up the numerical values, so G 110, 1 plus I, it will be 1.15. Now, number of years. So count from here. 1, 2, 3, 4, 5, 6. So it won't be 7, rather it will be 6. Minus I is 0.15 into 6 minus 1 divided by I 0.15 square of this into 1.15 to the power n is 6. If I just find out, so let me call this as, okay, let me use another color. So let me call this as, so what I am computing is the equivalence here. So let me call this as PB2. So it will be, okay, PB2. So PB2 will be equal to, so if I just compute it, comes out to be 873.04. Fine, but again we have computed this at t equal to 1, because originally we have this series, but we have manipulated in this way because only in this way we can use the standard relationship which is available. So this PB2 is eventually what we have calculated is at this point of time. Now again on similar lines, if I see, what do I have? I have 0 here, I have 1 here, and I am having a transaction here which is nothing but which is equal to PB2, which is of $873.04. Now if I just compute the value of, say, if I call this, if I am interested in finding out what will be the value of this transaction at time t equal to 0, so let me call this as PB2 dash. So it will be equal to, because f is given and I am interested in finding out p, of course number of years is equal to 1 and I is given as 15%. On similar lines what we did here, so it will be equal to 873.04 divided by 1.15 to the power 1. So this comes out to be 329.085. Fine. So now for this cash flow, if I am interested in finding what is the equivalent worth of all these transactions at this point of time, so I call this as PB. So PB will be equal to PB1 dash plus PB2 dash, because they are at the same time, so arithmetically we can add them. Since the arrows, both the arrows they are in the same direction, so we are adding them. If they are in opposite, then subtraction is to be done. So if I just write it down, so PB1 is 329.085 plus PB2 is 3 PB2 is 8 PB1, okay, 378. Okay, PB1 is, I think, PB2 is this I have, okay, so this is not 329. Please verify, this comes out to be 759.17. So PB1 is 329 plus, okay, call This is 759.17. So this is PB2 dash. So if I add the two, this comes out to be, if I add the two, this comes out to be 1088.255. So this is the net worth of all these transactions at time t equal to 0. Now if we wish to have the equivalence of these two cash flows, that means both should represent the same value at the same point of time. So here what we have done, we have computed the equivalent at 0, and here also we have computed the equivalent at 0. Now in order to have these two cash flows representing the same monetary value, this should be, so for equivalence, the condition is that PA should be equal to PB. So that is the condition for equivalence. So if I just equate, it will be 1.0688K equal to 108 1088.255. So from this, if I compute, K comes out to be $1018.20. So this should be the value of K in order to have the equivalence of these two cash flow diagrams. So this is how we have solved the problem. So this is all about the problem, how we have modified the various cash flows so that we can have a standard series, and we can use the relationships which we have discussed so far for calculating the equivalence of the cash flows given. Thank you very much. Hope you have enjoyed this problem solving session, and in the coming lectures I will be taking up some more problems, some more complicated problems where we can use these relationships to solve the present worth or the future worth or the annuities based problems. Once again, thank you very much.